Good morning. So we will start with the next topic, three-dimensional scaling. Okay, we have seen the basic transformation matrix transformations. We have three basic transformations, that is translation, rotation, and scaling. Translation is repositioning the object. It changes the position of the object. Okay. Next, we saw rotation. Rotation changes the orientation of the object. The size remains the same. Okay. Next, we see scaling. With scaling, we see that the size of the object varies. Okay. So first, we see we have already seen 2D scaling matrix. That is Sx Sy equal to Sx 0 0 0 Sy 0 0 0 1. Okay. The same 2D scaling is extended to 3D. Okay, that is a component for Z is added. So the 3D scaling matrix is like this. S equal to Sx 0 0 0 0 Sy 0 0 0 0 Sz 0 0 0 0 1. Okay, you know that this first column is for the x coordinate, the second column is for the y coordinate, the third column for the z coordinate, and the last one for the homogeneous coordinate. Okay, so here Sx, Sy, Sz are the three scaling factors. Sx is the x scaling factor, Sy y scaling factor, and Sz is the z scaling factor. Now suppose you have a point P, okay, and you want to scale this point using the scaling matrix S, then the scaled point P dash will be obtained by the multiplication of S and P. Okay. Now say P is XYZ, it is represented by the column vector XYZ1. Okay, so for a point, the homogeneous coordinate value is 1. So P is represented by the column vector XYZ1. Okay. Now, to get the scaled point P dash, that is with coordinates x dash, y dash, z dash, the column vector is x dash, y dash, z dash 1. Okay, that will be obtained by multiplying the scaling matrix by the point P. So in terms of equations, the x coordinate x dash is obtained by x into Sx plus y into 0 plus z into 0 plus 1 into 0. Since all are zeros, you get x dash equal to x into Sx. Similarly, you get y dash equal to y into Sy and z dash equal to z into Sz. Now we come to uniform scaling. Okay, what do we mean by uniform scaling? Uniform scaling is when all the three scaling factors are equal. That is Sx equal to Sy equal to Sz. Okay, when you have uniform scaling, the original shape of the object is preserved. Okay, you see you have a cube. Okay, say I scale by Sx equal to Sy equal to Sz equal to 2. Then this is the figure that I get. Okay, you see that the cube remains as a cube. Okay, now suppose our scaling parameters are not all equal, then the relative dimensions of the transformed object are changed. Okay, now you see this third figure which gives you the non-uniform scaling. X is scaled by 2, whereas y is scaled by 1.25. Okay, and z is again scaled by 1.3. Okay, so you see that the shape of the object has changed. The original shape is a cube. Now what you are getting is a cuboid. Okay, so if you have uniform scaling, the original shape of the object is preserved. Okay, whereas if you have non-uniform scaling, the shape changes. In addition to the shape, what we see is if you apply our scaling matrix, what we have just now defined, Sx 0, 0, 0, 0, Sy 0, 0, 0, 0, Z, Sz 0, 0, 0, 0, 1. If you apply that, we also see that the position of the object, changes relative to the coordinate origin. Okay, so if you have a scaling factor that is greater than 1, then you see that the object moves away from the origin. Okay, say this is our original object. I scale by a factor greater than 1, then this would be the object. You see that the x coordinate, you see that this x coordinate has changed from this position, from this position to this position. Okay, this x coordinate has changed from here to here. Okay, the object is not only enlarged, but it has also changed the position. Okay, the x coordinate, the distance from the origin in with respect to x-axis is only this, whereas for the scaled object, now it is this entire distance. Okay, same way with respect to y. With y, it is only this, whereas now it has changed to this. Okay, so you see that whenever you apply scaling, the size of the object varies, plus the position of the object also changes. Okay, now suppose you apply a scaling factor that is less than 1, a positive value but less than 1, then what happens? Yeah, if you apply a scaling factor less than 1, then the object moves towards the origin. Okay, a scaling factor of 1 greater than 1, we saw it moves away from the origin, whereas now if you apply a scaling factor that is less than 1, the object which was here now not only gets diminished or reduced in size, it also moves towards the origin. Okay, now can we have a scaling factor of 0? Scaling factor of 0 is not allowed. Okay, so scaling factor Sx, Sy and Sz can be positive. It has to be positive, and if it is greater than 1, we see that the object moves away from the origin. If it is less than 1, it moves towards the origin. Yeah. Now, this is our original object. Say we apply this scaling matrix, then we get this object. Okay, the object has not only enlarged with Sx, Sy, Sz greater than 1. We see that the object has enlarged and also moved away from the origin. But that is not always that we want. Okay, we want to only enlarge the object keeping some point fixed. For example, here, say this is the fixed point that I have. Okay, so I want to enlarge this object keeping this point fixed. That is, after enlarging, the coordinate corresponding to this point should remain in the same place, xf, yf, zf. Okay, how do we achieve this? Our scaling matrix Sx 0, 0, 0, 0, Sy 0, 0, 0, 0, Sz 0, 0, 0, 0, 1 is the scaling matrix with respect to the origin. That means if you apply this scaling matrix to any point in the coordinate system, the object is going to move away from the origin. Okay, it is no point is going to remain in the same place. Okay, whereas now what we want is 3D scaling about a selected fixed point. We want this point XF, YF, ZF to remain in the same position. Okay, so what do? We know the scaling matrix S, which is about the origin. Okay, so what we do is we use a sequence of transformations to achieve this scaling about the selected fixed position. Okay, so what we do, first we shift this fixed point to the origin. Since we know scaling about origin, we try to move this point to the origin. Okay, that is done by translation. Okay, so first we translate the object so that the fixed point XF, YF, ZF is now placed at the origin. Okay, now we know the scaling that is to be done with respect to the origin. That is, you apply the scaling matrix S. Okay, now once you apply, you are able to get the scaled object. Okay, here it is an enlarged the object has been magnified or enlarged. Okay, now what do? We don't want the object with in the point at the origin. We want it at XF, YF, ZF. So how do we achieve it? We translate the object back to the original position. Okay, that is, we inverse translate. We translate this object with this point in this position to this fixed position. We see that this point, which is at the origin, moves to this XF, YF, ZF. That is, we do the inverse translation of what we have done in the first step. Okay. So here, by how much do we translate in the first step? We have to move from XF, YF, ZF to origin. So that is, we translate by minus XF minus YF minus ZF. Okay. Next, we scale. Okay. We apply the scaling matrix, whatever is the scaling factor that we have. Okay. Next, we again inverse translate. That is, we have to move from origin to XF, YF, ZF. So we translate by XF, YF, ZF. Okay. Now, what is our, so in words, if you take, we translate the fixed point to the origin, we apply the scaling transformation, and then we translate the fixed point back to the origin. Okay. So what is our overall transformation matrix? Okay, we know that in order to get the overall transformation matrix, the leftmost term would be the last transformation that we have applied. Okay, that is translation by XF, YF, ZF. Okay, the next term would be the last but one translation. In our case, it is scaling, and so on. That is, we go in the reverse order. Okay, so our overall transformation would be M equal to this translation. Okay, translation by XF, YF, ZF, then scaling SX, Y, Z, SY, SZ multiplied by the first translation T of minus XF minus YF minus ZF. Now, what is the translation matrix when we translate by XF, YF, ZF? 1, 0, 0, XF, 0, 1, 0, YF, 0, 0, 1, ZF, 0, 0, 0, 1. The scaling matrix is SX 0, 0, 0, 0, SY 0, 0, 0, 0, SZ 0, 0, 0, 0, 1. Now the inverse translation, the translation matrix by minus XF minus YF minus ZF is 1, 0, 0 minus XF, 0, 1, 0 minus YF, 0, 0, 1 minus ZF, 0, 0, 0, 1. Okay. When you multiply these matrices, what you get is, this one. SX 0, 0, 0, 1 minus Sx into Xf, 0 Sy, 0, 1 minus Sy into Yf, 0, 0 Sz, 1 minus Sz into Zf, 0, 0, 0, 1. When you multiply these three matrices, this is what we get. Okay. So if you want to scale an object with respect to the fixed point Xf, Yf, Zf, we can apply this translate scaling, translate sequence of transformations, or we can directly apply this transformation matrix that we have obtained to the particular point X, Y, Z. So this completes our discussion on 3D